Alright, let's try out using the wishing game on an arguably trickier problem. So let's do the integral of x plus 1 over x squared plus 2 dx. Now, for those of you that might already know some calculus, sort of standard approach when you see a rational function like this is to try to factor the bottom and do something called partial fraction decomposition. But let's actually not do it that way, because it turns out there's a much shorter way to be able to do this problem using the wishing game. So let's go ahead and rewrite this. So we got the x squared plus 2x on the bottom, and it turns out this kind of looks a little familiar, because let's think of integral property that we know. So we know that if we have the integral of du over u, that ends up being the natural log of the absolute value of u plus c. And that's almost what we have here, right? So if you think of this as your u, this is the bottom part here, you got x squared plus 2x. In order to be able to use this particular shortcut and have the integral become the natural log, we need to have the derivative of what's on the bottom be on the top. And that's almost what we have, because the derivative of the bottom, the derivative of x squared plus 2x, is 2x plus 2. But we've got x plus 1. So, well, how can we fix that? Well, we can just throw on a 2 there. You say, gosh, if only there was a 2. We wish there was a 2 there. Because if there was a 2 there, then when you distribute that, you would get 2x plus 2, and that's what we want. Of course, we changed the problem by throwing on this 2. We wish for a 2, but to keep the problem the same, we have to balance it off by throwing a 1/2 on the outside. But now it looks like exactly what we need. So we still have this 1/2 that's here, so we got to write that down. But what does the rest of this integral become? Well, it exactly matches this format. So we've got a formula on the bottom. On the top, we've got the derivative of the bottom sitting out there. So it ends up, it's just going to be the natural log of the absolute value of, u. But what's u? It's the formula on the bottom, which is this. So natural log of x squared plus 2x. And of course, we have to throw on the plus c. Let's try our hand at a somewhat trickier U-substitution problem. So let's do the square root of 1 plus x squared times x to the 5th dx. So one thing to notice, and this is why I put this little tail at the end of the square root, is just to indicate that this is where the square root stops. So the only thing underneath the radical is the 1 plus x squared. The x to the 5th is outside the square root. One thing that sometimes students try to do is to simplify the square root by taking the square root of each part. That is algebraically invalid. You cannot do that. So you can't do the square root of 1 is 1 and the square root of x squared is x. Incidentally, the square root of x squared is not x anyway. It's the absolute value of x. But that aside, you cannot split up a radical across a plus sign like that. So it turns out it is possible to use the wishing game on this, but it's pretty tricky to see what you should wish for. So instead, let's do this with U-substitution. Now, a common question is, well, what should we let u be? So should u end up being x to the 5th? Should it be x squared? Should it be 1 plus x squared? Should it be the square root of 1 plus x squared? And often what I tell students is, eventually after doing enough of these problems and practicing, you will get a good feel for what u should be. And there's no harm in just trying something and seeing that it doesn't work, because maybe it just doesn't end up simplifying it. But that's okay, so I'm going to go ahead and try something here. So one thing I notice is that, well, it would be nice if this thing under the square root simplified. We just can't do it right now because there's a plus there. So how about we let this be our u? So that way it's just one thing under a square root instead of two things added together. So you just come over here, make sure you declare what you're going to have u be. So u is going to be 1 plus x squared. And we're going to have to solve for x at some point for when we do the substitution. So to solve for x, we're going to scoot the 1 over. So u minus 1 is x squared. And then we have to square root both sides there. So x is going to be u minus 1 to the 1/2 power. So there's our x. So now let's actually figure out what the dx is. And this is actually why I solved for x in the first place. So dx, just using the power rule on this. So remember, fall off the cliff, lose a life. So 1/2 u minus 1 to the negative 1/2 power du by the chain rule. So, all right, now I guess we're ready to substitute in for our integral. So instead of x's, we're going to have everything be u's. So let's just take this one step at a time. So the square root of 1 plus x squared just becomes the square root of u, because 1 plus x squared is u. And I just wrote it without the square root. I wrote it as 1/2. Makes it easier to do the power rule later on. So all of that was just this part. Now we have to deal with x to the 5th. Well, don't forget what x is. X is u minus 1 to the 1/2 power. So when we raise that to the 5th, it's all this to the 5th, but a power raised to a power just multiplies the exponents. So what you end up with is u minus 1 to the 5/2 power. That's what x to the 5th becomes. And a lot of times students just leave it at that. They think, okay, I've done the substitution, but don't forget we've got this dx here, and dx is actually all of this. So we also have to write that down. So thankfully, we can simplify this big horrible mess, because it looks like the problem just got worse. So it's like, okay, we had sort of two things multiplied together. Now we've got three things multiplied together, but actually it's not as bad as all that. So we still got the u to the 1/2, but notice now here we've got a u minus 1 to the 5/2 times a u minus 1 to the negative 1/2 power. I'm going to ignore this 1/2 right now because we could always pull that outside the integral later. So the bases are the same. So when the bases are the same, you add the exponents together. So it's u minus 1 to the 5/2 plus negative 1/2. Hey, that's just 2, right? 2.5 take away a half is 2. So it's u minus 1 squared. And now I'm going to go ahead and, so that was these two put together. And now the 1/2 I'm going to pull it outside. And don't forget we still have the du hanging out there. So we got the du, the 1/2 on the outside. This still looks kind of problematic, but at least we accomplished what we wanted to, because now underneath the square root, instead of two things added together, is just one thing. Of course, the sacrifice we made to get that is now before we just had a one thing to a power. Now it's two things to a power. But, you guys see what's going on here? This is easy to compute, right? This thing, when the two things were underneath the square root, couldn't do anything with it. We had to substitute. But now we've got two things under a nice whole power, and that we can just FOIL out. So u minus 1 squared, that's just u squared minus 2u plus 1. So we can go ahead and now distribute this. So we've got a u to the 1/2 in front of this yellow stuff right here. So if we multiply that out, so don't forget we still have the 1/2 out in front, right? So this 1/2 is still out there. But when you distribute the 1/2 in front of all this, it's u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. I'm getting a little lazy here and just tacking on this du. The du at the end really goes to all of this entire integrand. It's actually not uncommon for mathematicians to get lazy and not bother to put parentheses here. I guess I'll go ahead and do it. The peer pressure got to me there. But it's actually okay if you leave it out. There's no risk of confusion. No one's going to think that you only meant the du on this. So everyone knows it's for the entire integrand. All right, well now we know how to integrate this, right? We still have the 1/2 hanging out there in front, and now we just have to do the power rule on each of these three things. So the power rule on u to the 5/2, so add 1, divide by the new exponent. So when you add 1 to 5/2, it becomes 7/2. Divide by that new exponent, but dividing by 7/2 is the same thing as multiplying by 2/7. So I'm just going to write that in front. So that was the integral of that part. Now we got to integrate this. So the minus 2, just a coefficient. I'm going to write it down. We don't need to worry about it. The u to the 3/2, again, add 1, divide by the new exponent. So I add 1 to 3/2, it becomes 5/2. Divide by the new exponent, dividing by 5/2 is multiplying by 2/5. So we're going to multiply by 2/5 there. And last but not least, we've got this part right over here. Again, just another power rule. So add 1, u to 3/2, and then multiply by 2/3. Technically, we're done with all the integrals, but I'm going to go ahead and write on that plus c here. And don't forget, this is all in front of a 1/2, so I'm going to multiply this through. Also simplify a little bit as I go. But when I simplify, remember I can't leave my answers with u's. U's is something we just made up ourselves. The original problem asked about x's. So wherever I see a u, I actually have to rewrite the u as 1 plus x squared. So all right, I'm going to go ahead and do that. So got to distribute this out. Well, 1/2 times 2/7, the 2's are just going to cancel. So I'm going to have 1/7. But instead of saying u to the 7/2, I'm going to say 1 plus x squared to the 7/2. And I just keep on doing this, right? So I just keep on, all right, distribute this out, simplify as I go, replace the u with 1 plus x squared. So 2/5, 1 plus x squared to the 5/2, and then distribute the 1/2 one more time. So again, the 2's cancel here, right? So the 2 there and the 2 there cancel. You'll have 1/3 u, which is really 1 plus x squared, to the 3/2, and then don't forget that plus c, and that's it. We finished. Now, if you really wanted to double check this, what you could do is take the derivative of all of this And my claim is if you take the derivative of this and simplify it, it will actually simplify back to this. But I will leave that as a problem for the viewer.